The universe is a vast and ancient theater where the most profound stories are written in the light of distant suns, serving as the fundamental engines where primordial gas transforms into the chemical building blocks of life. This transition is not merely a physical process but a cosmic alchemy known as nuclear synthesis, occurring in the crushing pressures of stellar hearts. It is here that the very atoms that make up our existence were first forged, a concept that connects every human being to the furthest reaches of the Milky Way. Carl Sagan famously observed that humans are, in both a literal and a deeply poetic sense, star stuff, because the nitrogen in our DNA, the calcium in our teeth, and the iron in our blood were once part of collapsing stellar bodies. When we look at the night sky, we are not just looking at points of light, but at our own ancestral origins, observing the furnaces that created the world we inhabit. This biological link to the cosmos provides a sense of wonder and curiosity that drives our scientific exploration. Among the countless lights in the sky, dwarf stars present a unique and enduring paradox for modern astronomy, as they are the most common celestial objects in the universe yet remain remarkably elusive. Their low luminosity hides them from all but our most sensitive instruments, creating a dark population of stars that outnumbers everything else in the galaxy. This elusive nature makes them difficult to categorize, sitting at the boundary of what we consider to be a true star. There is a fundamental distinction between the true stars that sustain themselves through the fusion of hydrogen and the failed stars, or brown dwarfs, that occupy a strange gray zone. These substellar objects are larger than gas giant planets like Jupiter, but do not possess the mass required to ignite the fires of nuclear fusion in their cores. They are the missing link between the worlds we know and the suns we orbit, defying easy classification by traditional astrophysical models. Neil deGrasse Tyson has often pointed out the deceptive and extreme scale of these objects, particularly white dwarfs, which can compress the mass of the entire sun into a volume no larger than the Earth. This creates a material of such incredible density that a single teaspoon would weigh as much as an entire fleet of elephants, challenging our intuition about the nature of matter. These stars are essentially giant, cooling crystals, protected from collapse by the strange laws of quantum mechanics. Beyond their physical extremes, dwarf stars serve as critical, cosmic clocks and archaeological relics for researchers trying to piece together the history of our galaxy. By studying the coolest and oldest dwarfs, scientists can look back into the early formation of the Milky Way and predict the eventual destiny of our own solar system. They are the silent witnesses to billions of years of cosmic history, holding the secrets of the past and the clues to the future. However, as our technology improves, we are finding that these stars are even more mysterious than we previously imagined, presenting persistent anomalies that challenge our current models of stellar evolution. From impossible orbital tilts to unexpected chemical compositions, the data coming from our greatest telescopes often contradicts our mathematical expectations. These gaps in our knowledge suggest that there are fundamental rules of the universe that we have yet to fully understand. We find ourselves at the border between the known and the unknown, peering into the darkness with eyes open not in fear but in wonder, as Brian Cox often reminds us. Science is the practice of exploring these secrets, and the dwarf stars offer some of the most compelling challenges in the modern era of discovery. To understand them is to understand the life cycle of the cosmos itself, from its vibrant birth to its eventual, quiet conclusion. The search for the first brown dwarf was a decades-long quest that finally saw success in 1995 with the discovery of Gliese 229b at the Palomar Observatory. This object was hailed as a revolutionary find, as it provided the first clear evidence of a substellar body with a methane-rich atmosphere similar to that of Jupiter. For nearly 30 years, it served as the poster child for the entire class of brown dwarfs, representing the definitive link between planets and stars. However, Gliese 229b carried a scientific mystery that troubled astronomers for decades, as it appeared to be significantly dimmer than its measured mass should have allowed. Based on its gravitational influence on its host red dwarf star, Gliese 229a, researchers estimated its mass to be approximately 70 times that of Jupiter. According to evolutionary models, an object of this mass should have been much brighter in the infrared spectrum than what was actually observed. This discrepancy led to intense debate and the development of various theories to explain why Gliese 229b was so lackluster in its brightness. Some scientists suspected that the cooling models for substellar objects were fundamentally flawed, or that the object possessed unusual atmospheric properties that trapped its internal heat. Others hypothesized that the age of the system had been incorrectly determined, as brown dwarfs dim predictably as they get older. The resolution to this long-standing paradox finally came in 2024 through the use of the gravity interferometer and the Cry-Res Plus spectrograph at the Very Large Telescope in Chile. By combining the light from 4 massive 8-meter telescopes, astronomers were able to see much finer spatial details than had ever been possible before. The new data revealed that what was once thought to be a single object was actually a pair of tightly bound, twin brown dwarfs. Now designated as Gliese 229Ba and Gliese 229Bb, these twins orbit each other every 12 days at a separation of only 16 times the distance between the Earth and the Moon. This binary nature immediately resolved the luminosity paradox, as the observed light was the combined output of two smaller, less massive objects. Specifically, the pair consists of one dwarf with 38 Jupiter masses and another with 34 Jupiter masses, which matches theoretical brightness predictions perfectly. The existence of such a tight and compact binary system raises profound questions about the formation mechanisms of these failed stars. While they were previously thought to form from the fragmentation of large gas clouds, the process that would create two such seeds in such close proximity is still being studied. This discovery suggests that many other supposedly lone brown dwarfs in our catalogs may actually be hidden binaries that our current telescopes cannot resolve. The implications for astrophysics are significant, as it may mean that our current estimates for the total mass distribution of substellar objects in the Milky Way are incorrect. If a large percentage of brown dwarfs are actually binaries, we must rethink how we calculate the initial mass function, which describes how many objects of different masses are born in the galaxy. Gliese 229b, once the singular standard for its class, has now become a benchmark for the complexity of substellar systems. This discovery highlights the exhilarating nature of astronomy, where even the most famous objects can hold secrets that stay hidden for 30 years. By revisiting old mysteries with more powerful instruments, we are able to correct our models and deepen our understanding of the universe's most elusive residents. The story of Gliese 229b is a testament to the persistence of scientific inquiry and the constant refinement of our cosmic knowledge. White dwarfs are the dense and silent stellar embers that remain after approximately 95% of all stars, including our Sun, have exhausted their nuclear fuel. When a star of this size can no longer sustain the fusion of hydrogen or helium, it undergoes a dramatic transition, shedding its outer layers into space. What remains is an extremely hot and compact core that no longer produces energy through traditional means, but instead begins a journey of cooling that lasts for trillions of years. Unlike main sequence stars, which are held up by the outward pressure of thermal heat generated by fusion, white dwarfs are supported by a strange quantum mechanical force. This is known as electron degeneracy pressure, which arises from the Pauli exclusion principle, a fundamental law of physics stating that no two electrons can occupy the same quantum state at the same time. In the incredible density of a white dwarf, the electrons are squeezed together so tightly that they create an outward pressure that resists further collapse. This quantum support creates a quantum fortress that is independent of the star's temperature, allowing the white dwarf to remain stable even as it loses its heat to the vacuum of space. However, this leads to a counterintuitive relationship where the radius of a white dwarf actually decreases as its mass increases. The more mass you add to one of these stars, the more its internal gravity crushes the degenerate matter, forcing it to become smaller and even denser. There is a theoretical upper limit to this stability, a point beyond which the quantum pressure can no longer hold back the force of gravity. This boundary is known as the Chandrasekhar limit, calculated by Subrahmanyan Chandrasekhar to be approximately 1.44 times the mass of the Sun. If a white dwarf exceeds this critical mass, typically by stealing material from a nearby companion star, it will collapse, potentially triggering a catastrophic Type 1a supernova explosion. The mystery for modern astronomers lies in the observation of ultramassive white dwarfs that seem to push right up against or even challenge this 1.44 solar mass limit. For example, the discovery of WD0525 plus 526, which has a mass of 1.2 times that of the Sun, suggests that these heavy remnants are more common than we previously believed. These massive objects are often thought to be the products of stellar mergers, where two smaller white dwarfs collide and combine their mass into a single, dense body. Understanding the precise physics of these limits is essential, as Type 1a supernovae are used as standard candles to measure the expansion rate of the universe. If our models of how white dwarfs approach and exceed the Chandrasekhar limit are incomplete, our measurements of cosmic distances and dark energy could be affected. The study of these stars is therefore not just about stellar death, but about the fundamental constants of the cosmos and the ultimate expansion of space. Furthermore, the extreme conditions inside a white dwarf allow scientists to test physics that cannot be replicated on Earth. The state of degenerate matter is so dense that it behaves like a cold Fermi gas, where quantum effects dominate the large-scale behavior of the star. Every massive white dwarf we find is a laboratory for high-energy physics, providing data that helps us understand how matter behaves under the most intense pressures imaginable in the known universe. The legacy of Subrahmanyan Chandrasekhar's work continues to guide our exploration of these objects, but the anomalies we find today show that there is still much to learn. As we discover more ultramassive dwarfs and merger remnants, we are forced to refine our understanding of the boundary between stability and explosion. The white dwarf is far from being a simple, dead star. It is a complex and enduring puzzle of the quantum world, holding the line against gravity for billions of years. The study of brown dwarfs is frequently hindered by a fundamental challenge, known as the age-mass degeneracy problem. Because these failed stars lack a stable internal engine like hydrogen fusion, they cool and dim continuously throughout their entire existence. This means that a young, low-mass brown dwarf can have the exact same temperature and brightness as an older, high-mass brown dwarf, making it impossible to determine an object's true nature just by looking at it. To solve this paradox, astronomers search for benchmark systems where the age of the objects can be determined through independent means. One of the most significant discoveries in this field is the hierarchical system UPM J1040-3551, located approximately 82 light-years from Earth. This rare system consists of a pair of cold brown dwarfs that are gravitationally locked in an orbit around a pair of young red dwarf stars. This configuration provides a unique cosmic laboratory for testing our evolutionary models. Because the red dwarfs in the system are true stars that burn hydrogen, their ages can be measured with high precision using established stellar models. Since it is highly likely that all four objects formed at the same time from the same cloud of gas, the red dwarfs serve as a chronometer for the brown dwarfs. By pinning down the age of the system, estimated to be between 300 million and 2 billion years, scientists can finally calculate the true masses of the substellar companions. In the case of UPM J1040-3551, the brown dwarfs are extremely cold, with temperatures of only 550 degrees Celsius and 420 degrees Celsius, yet they are quite massive, weighing between 10 and 30 times more than Jupiter. These T-type brown dwarfs represent a critical mass range that bridges the gap between massive planets and small stars. Finding them in such a complex system allows researchers to calibrate their atmospheric and cooling models, which can then be applied to millions of other isolated brown dwarfs. However, the configuration of the UPM J1040-3551 system itself is a mystery of galactic dynamics, as the two pairs are separated by a vast distance of 1,656 astronomical units. The orbital period for the entire system is estimated to be over 100,000 years, meaning we will never see these objects complete a single revolution in human history. How such a wide and hierarchical system forms and remains stable in the chaotic environment of a star cluster is a question that challenges current theories of star formation. The discovery was made possible by the Gaia space mission, which tracks the positions and motions of stars with unprecedented accuracy. By analyzing how the objects in UPM J1040-3551 move together through space with the same velocity and direction, astronomers were able to confirm that they are truly bound together. This system is the first of its kind ever found, demonstrating that the diversity of stellar and substellar arrangements in our galaxy is far greater than we once imagined. Every new benchmark system like this helps to resolve the age-mass paradox and brings us closer to a full census of the Milky Way's population. Without these hierarchical systems, our understanding of brown dwarfs would remain based on educated guesses rather than hard data. By using the light of red dwarfs to illuminate the mysteries of their darker companions, we are slowly unraveling the complex history of how stars and planets are born together. The standard theory of white dwarf structure dictates that their atmosphere should be remarkably pristine, composed only of the lightest gases like hydrogen or helium. Because white dwarfs have such immense surface gravity, any heavier element like iron or magnesium should sink into the interior and disappear from view within a matter of weeks. This process, called gravitational settling, creates a naturally pure surface that should theoretically never show any signs of heavier chemistry. However, reality has proven to be much more complex, as observations show that between 25 and 50% of white dwarfs are polluted with a variety of heavy metals. This pollution can only be explained if the white dwarf is actively consuming material from its surrounding environment, pulling in debris that replaces the elements that have sunk into its core. This discovery has given birth to the fascinating field of necroplanetology, the study of the remains of dead planetary systems. The The source of this heavy metal pollution is widely believed to be the fragments of planets, asteroids, and comets that survived the star's initial expansion into a red giant. As the star evolved and shed its mass, the gravitational balance of the system was shattered, sending surviving bodies into chaotic and unstable new orbits. Some of these objects eventually drifted too close to the white dwarf and were torn apart by tidal forces, creating a disk of dust that slowly rains down onto the star's surface. By analyzing the specific fingerprints of these metals in a white dwarf spectrum, astronomers can actually determine the chemical composition of the worlds that were once in orbit. For instance, the 10-billion-year-old white dwarf W.D.J. 2147-4035 shows a unique enrichment of lithium and potassium, elements that are rare in our own solar system. This suggests that planetary systems in the very early history of our galaxy were made of building blocks that differ significantly from those that form the Earth. In contrast, another star called W.D.J. 1922+0233 appears to be consuming material that is remarkably similar in composition to the Earth's continental crust. These observations prove that rocky, Earth-like planets are a common outcome of the star formation process across cosmic time. The planetary graveyards found around these stars show that the ingredients for habitable worlds have been present in the Milky Way for at least 10 billion years, long before our Sun even existed. This research also provides a somber look into the future of our own solar system. In several billion years, when the Sun becomes a white dwarf, it will likely consume the inner planets, and its atmosphere will become polluted with the iron and silicon of the Earth. We are seeing the ultimate fate of civilizations and worlds played out across the galaxy, as the dead hearts of stars preserve the chemical memory of everything they have destroyed. Despite these insights, many mysteries remain in the field of necroplanetology, such as why some white dwarfs remain pristine while others are heavily polluted. Some studies suggest that the rate of accretion depends on the presence of giant planets that act as gravitational shepherds, pushing smaller debris into the star. Others investigate whether the pollution could be caused by the accretion of interstellar gas or the remnants of a close binary companion that was also torn apart. As we improve our spectroscopic tools, we are beginning to see a vast diversity in the structure and evolution of these ancient planetary systems. Every polluted white dwarf we find is a unique window into a lost world, allowing us to reconstruct the mineralogy and geology of planets that died billions of years ago. Necroplanetology is turning the ashes of stars into a library of the cosmos, showing us that our own world is just one chapter in a much larger story of birth, death, and chemistry. The discovery of carbon in the atmosphere of the ultramassive white dwarf W.D. 0525+526 has provided astronomers with a smoking gun for the theory of violent stellar mergers. Under normal conditions, a white dwarf that forms from a single star is expected to have a thick envelope of hydrogen and helium that completely hides the star's carbon-oxygen core from our view. The fact that carbon is visible on the surface of WD 0525+526 implies that its original protective layers were either stripped away or burned off during a massive collision. The 0525+526 is a remarkable object, located 130 light-years away with a mass that is 20% larger than our Sun. With a surface temperature of nearly 21,000 Kelvin, it is significantly hotter than most other known white dwarfs, which typically cool down to much lower temperatures after their formation. This extreme heat presented a puzzle for researchers, as standard convective mixing, the process that brings core material to the surface in cooler stars, cannot occur at such high temperatures. To solve this mystery, the team of astronomers identified a much more subtle and rare process called semi-convection that is occurring in WD 0525+526.1. This is the first time semi-convection has been observed in a white dwarf, and it explains how tiny amounts of carbon can slowly drift upward through a very thin hydrogen-helium shell. This process creates a much slower and more partial mixing than regular convection, leaving a distinct chemical signature that can only be seen with the most sensitive instruments. The detection was only possible because of the Hubble Space Telescope's unique ability to observe ultraviolet light. Invisible light, WD 0525+526, looks like a heavy but otherwise ordinary white dwarf with a pure hydrogen atmosphere. However, the ultraviolet spectrum revealed faint carbon lines that were invisible to optical telescopes, unmasking the star's true identity as a merger remnant. This suggests that many other supposedly normal white dwarfs might actually be hiding a violent history that we have yet to uncover. The implications of this discovery are profound for our understanding of binary star systems and the frequency of cosmic explosions. If mergers are more common than previously thought, They could be a significant source of Type 1a supernovae, which occur when a merger remnant exceeds the stable mass limit. By identifying objects like WD0525 plus 526 in their early stages, scientists can build better models of how these collisions unfold and how they enrich the galaxy with heavy elements. Furthermore, the thinning of the hydrogen and helium layers in WD0525 plus 526, measured to be 10 billion times thinner than in typical white dwarfs, provides a direct look into the aftermath of a stellar crash. It confirms that the energy of the merger is enough to strip away most of the star's outer envelope, leaving a bare core that begins its life anew. This violent creation story distinguishes merger remnants from stars that simply die of old age, adding a new chapter to the study of stellar evolution. As WD0525 plus 526 continues to cool over the next several billion years, more carbon is expected to emerge at its surface through standard convection, eventually making it resemble the other known merger products. For now, its ultraviolet glow offers a rare and precious glimpse into the earliest stage of a merger's aftermath, acting as a benchmark for the end-of-life scenarios of binary stars. It reminds us that the galaxy is a place of dynamic and often destructive encounters that reshape the population of stars. The discovery of this masquerading merger remnant highlights the necessity of space-based observations and the continued importance of the Hubble mission. Without the ability to see the ultraviolet fingerprints of carbon, we would remain blind to the violent processes that create some of the most massive and extreme objects in our neighborhood. Every ultramassive white dwarf we find is a potential relic of a past collision, holding the key to the frequency and impact of stellar mergers across the universe. In the vast catalog of brown dwarfs, few objects are as puzzling to astronomers as CW89AB, a body that defies our most basic evolutionary models. This brown dwarf was discovered orbiting a Sun-like star in the Ruprecht 147 cluster, which provided scientists with a rare opportunity to measure its mass, radius, and age independently. Because the cluster's age is known with high precision to be 3 billion years, CW89AB was expected to be a standard case for checking how substellar objects cool over time. However, when the Spitzer Space Telescope observed CW89AB as it passed behind its host star, the results were shocking. The depth of the secondary eclipse showed that the brown dwarf was 16 times brighter at certain infrared wavelengths than anyone had predicted. While standard models suggested that an object of its age and mass should have an internal temperature of about 850 Kelvin, the observed brightness indicated a temperature of 1700 Kelvin. This massive discrepancy of nearly 1000 degrees has created what is known as the overluminous enigma, as there is no obvious reason for the star to be so hot. Scientists first investigated whether the host star was simply heating the brown dwarf's atmosphere, but calculations showed that even the most extreme stellar irradiation could not account for a temperature of 1700 Kelvin. Furthermore, such intense heating would have caused the brown dwarf to expand, but its measured radius remains perfectly consistent with standard models. One of the leading theories for this anomaly is the existence of a temperature inversion in the brown dwarf's atmosphere. In this scenario, the upper layers of the atmosphere are actually hotter than the layers below them, a phenomenon often seen in hot Jupiter planets that are very close to their stars. However, CW89AB is not in an extreme enough orbit for this to happen through normal means, leading researchers to look for more exotic causes. A potential cause for such an inversion could be a superstellar ratio of carbon to oxygen in the brown dwarf's atmosphere. If there is an overabundance of carbon, it could create a blanketing effect that prevents the object from radiating its internal heat away efficiently. This would mean that CW89AB has stayed hot for billions of years longer than it should have, challenging our assumptions about how the atmospheres of substellar objects evolve and retain energy. If this theory is correct, it has major implications for how we think brown dwarfs are formed. A high carbon-to-oxygen ratio is often a sign of core accretion, the process by which planets form in a disk, rather than gravitational collapse, the process by which stars form. This would mean that CW89AB is effectively a massive planet masquerading as a brown dwarf, further blurring the line between these two types of celestial bodies. The mystery of CW89AB is currently an unsolved case that requires more data from the James Webb Space Telescope. High-resolution spectroscopy is needed to determine the exact chemical ratios in its atmosphere and to see if the glowing methane seen in other brown dwarfs is also present here. Until then, this overluminous object remains a fundamental challenge to our understanding of stellar physics, suggesting that our cooling models may be missing a critical component. Every time we find an object like CW89AB that doesn't fit the rules, it forces us to rethink the entire system of how stars and planets are classified. It reminds us that the universe is far more diverse and complex than our mathematical models often allow. Whether it is a temperature inversion, a chemical anomaly, or a flaw in the physics of cooling, CW89AB is a shining example of the many mysteries that still linger in the dark corners of our galaxy. In April 2025, astronomers using the Very Large Telescope in Chile announced a discovery that defied all standard expectations of how planetary systems are arranged. They found an exoplanet, named 2M1510ABB, that orbits a pair of young brown dwarfs at a perfect 90-degree angle. This means the planet flies directly over the poles of its two suns, a configuration known as a polar orbit that had never been clearly detected in a circumbinary system before. This discovery is a radical twist on the classic image of the twin-sun planet Tatooine from science fiction. In our own solar system and most others we have studied, all the planets orbit in a flat plane that matches the equator of their host star, which is a natural result of how they form from a spinning disk of dust. The existence of 2M1510AB suggests that this orderly arrangement is not the only way a system can exist, and that the universe can be far more chaotic. Researchers believe that the polar orbit was likely caused by a violent gravitational interaction in the system's early history. The 2M1510 system actually contains a third brown dwarf in a very distant orbit, which could have acted as a gravitational perturber. Through a process called the Kozai-Ledov mechanism, the gravitational pull of a distant third body can cause the orbit of a closer planet to tilt and oscillate wildly over millions of years. In some cases, this mechanism can flip a planet's orbit by 90 degrees or more, effectively putting it into a permanent polar path. The fact that 2M1510AB has survived in this orientation around such low-mass objects as brown dwarfs is particularly incredible. Brown dwarfs have much weaker gravity than stars like our Sun, making their planetary systems much more vulnerable to being completely disrupted or ejected during such violent shifts. The planet was detected not through direct imaging, but by carefully measuring the wobble of the two central brown dwarfs. Astronomers noticed that the orbits of the brown dwarfs were rotating or precessing in a way that could only be explained by the gravitational tug of a third object in a perpendicular orbit. This delicate detection was made possible by new analysis methods that improved measurement precision by a factor of 30, allowing the team to see the subtle signs of the planet's presence. The discovery of the 2M1510 polar orbit proves that the universe is a place where even the most extreme and unlikely configurations can and do exist. It challenges our computer simulations of how planets form and survive in multiple star systems, showing that we have likely underestimated the diversity of planetary architectures. If planets can survive in polar orbits around brown dwarfs, they might be found in even stranger places across the Milky Way. Furthermore, this system serves as an important benchmark for studying the youth of brown dwarfs, as 2M1510 is part of the Argus moving group and is only about 45 million years old. This early stage of evolution is a critical time for understanding how orbits stabilize or collapse. By observing how 2M1510AB interacts with its host stars, scientists can learn more about the longevity of chaotic systems and the long-term fate of perpendicular worlds. The 2M1510 system is a reminder that the dark regions of our galaxy are filled with real-life twists that keep us questioning our understanding of physics. As we continue to look for more polar planets, we may find that our own orderly solar system is the exception rather than the rule. The chaotic dance of the 2M1510 system is a testament to the unpredictable and fascinating nature of the cosmos, where gravity is always finding new ways to surprise us. One of the most fundamental questions in modern astrophysics is defining the lower limit of what constitutes a star, a problem often called the mass limit dilemma. Conventionally, stars form top-down from the gravitational collapse of massive clouds of gas, while planets form bottom-up from the dust and gas left over in a disk around those stars. However, the discovery of free-floating brown dwarfs has blurred the lines between these two distinct formation paths. Recently, using the James Webb Space Telescope, astronomers identified a free-floating brown dwarf in the IC 348 star cluster with a mass only 3 to 4 times that of Jupiter. This is well within the mass range of what we consider to be giant planets, yet this object is not orbiting any star. It is drifting alone through the cluster as an independent entity. The existence of such a tiny object challenges our current theories of star formation, as it is difficult for such a small mass of gas to collapse on its own. This discovery raises the question of whether these objects are rogue planets that were ejected from their original solar systems, or star seeds that formed directly from a cloud of gas. If they are indeed formed like stars, it means that the process of gravitational collapse is far more efficient at small scales than we ever imagined. It would imply that there is a continuous spectrum of objects from the most massive stars down to bodies that are smaller than the planet Jupiter. Furthermore, the atmospheres of these tiny brown dwarfs have revealed unexpected chemical complexity. Webb detected an unidentified aliphatic hydrocarbon, a carbon-containing molecule that is not predicted by any current models for such low temperatures. This mystery molecule suggests that the chemical processes occurring in the coldest brown dwarfs are much more diverse and active than we previously thought, potentially overlapping with the chemistry found in the atmospheres of giant planets. The IC 348 cluster is an ideal laboratory for studying this dilemma because it is relatively young and nearby. Astronomers have found multiple objects there that are less than 8 times the mass of Jupiter, suggesting that these tiny dwarfs are not just rare anomalies but a common product of the cluster environment. This challenges the idea that a certain minimum mass is required to initiate the star formation process, as nature seems to find a way to create objects at all scales. If the galaxy is indeed teeming with these tiny rogue worlds, it could significantly change our understanding of the total mass of the Milky Way. Because they are so small and cold, they emit almost no visible light and can only be seen in the infrared, meaning they have likely been hidden from our view for most of history. The James Webb Space Telescope is now opening a new window onto this hidden population, revealing a universe that is far more crowded with substellar objects than we once believed. The study of these objects also connects to the broader question of how the chemical ingredients for life are distributed. The presence of complex organic molecules and H.S in the IC 348 cluster shows that the building blocks of life are present in the same environments where these tiny dwarfs are born. This suggests that the potential for complex chemistry is a universal feature of gas clouds, regardless of whether they produce a massive star or a tiny, drifting world. Ultimately, the mass limit dilemma is a reminder that our scientific categories are often human constructions that nature does not always follow. Whether we call these objects failed stars or rogue planets, they represent a fascinating frontier of research that bridges the gap between different fields of astronomy. As we find more of these tiny seeds, we are forced to rewrite the rules of star formation and to reconsider the sheer diversity of the celestial bodies that populate our galaxy. The study of dwarf stars has recently taken a surprising turn with the detection of periodic radio signals from the system known as LTJ 1101.1 every 125.5 minutes. This source emits a bright pulse of radio waves that has captured the attention of astronomers worldwide. Unlike typical pulsars, which are rotating neutron stars that emit radio beams as they spin, LTJ 1101 is a binary system consisting of a white dwarf and a red dwarf orbiting each other. The periodicity of the radio pulses matches the orbital period of the two stars exactly, which is the smoking gun for a new type of stellar interaction. Researchers believe the signal is generated by the magnetic fields of the white dwarf and red dwarf as they whip around each other in an extremely tight orbit. This magnetic interaction acts as a superhighway for plasma, which is accelerated to relativistic speeds and released as a burst of coherent radio emission. This phenomenon is remarkably similar to the interaction between Jupiter and its moon Io, where Io's movement through Jupiter's magnetosphere creates powerful radio pulses. In the case of LTJ 1101, the system is a much more powerful, stellar-scale version of this unipolar inductor mechanism. This discovery provides the first direct evidence that the orbital motion within a binary system can power long-period radio transients, a class of signals that was previously a mystery. The discovery was first made by combing through archival data from the Low-Frequency Array, LOFAR, the largest radio telescope of its kind. Astronomers found that the pulses were intrinsically variable, appearing in some observations but not in others, which suggests that the magnetic superhighway is not always active. This variability may be linked to the magnetic activity of the red dwarf companion, which can flare and disrupt the connection between the two stars. By analyzing these radio pulses, scientists can measure the strength and orientation of the star's magnetic fields with unprecedented precision. This is especially important for understanding how magnetic fields are generated in low-mass stars, a process that is thought to be fundamentally different from that of the Sun. The high level of magnetic activity in dwarf stars is often responsible for the massive flares that can strip the atmospheres of nearby planets, making it a critical factor in the search for life. The ILTJ 1101 system is part of a newly recognized population of galactic radio sources that includes other long-period transients like Gliese J1627-52.58 before this discovery. Such long-period pulses were only thought to come from exotic magnetars or isolated spinning stars. Now, we know that binary interactions are a major source of these signals, opening up a new way to identify and study white dwarf and red dwarf systems across the galaxy. This interaction may also play a key role in the long-term evolution of binary systems. The magnetic drag, created by the unipolar inductor effect, can drain orbital energy, causing the two stars to migrate closer together over time. This can eventually lead to the stars merging or to the white dwarf beginning to siphon material from the red dwarf, turning the system into a cataclysmic variable. The radio pulses of ILTJ 1101 are the early warning signals of this dramatic future. The repeating radio transients of the dwarf stars show that the universe is a far noisier and more interactive place than we once imagined. They reveal the invisible ties of magnetism that bind stars together, and they provide a new tool for probing the extreme environments of the Milky Way. As we detect more of these signals, we are beginning to map out the magnetic superhighways of our galaxy, one pulse at a time, revealing the secret lives of the stars that hide in the dark. Among all the stars in the cosmos, red dwarfs are the ultimate marathon runners, possessing a longevity that defies human comprehension. Because they are relatively small and cool, they burn their hydrogen fuel at an incredibly slow rate compared to massive stars like our Sun. Furthermore, they are fully convective, meaning they constantly mix their hydrogen from the outer layers into the core, ensuring that every drop of fuel is eventually used. This efficiency means that red dwarfs can live for trillions of years, a time span that is much longer than the current age of the universe. In fact, every red dwarf ever born in the 13.8 billion-year history of the galaxy is still shining today, and they will continue to be the primary source of light in the universe for an unimaginable amount of time. They are the silent, enduring survivors of the cosmos, outlasting all the more brilliant and violent stars. As these stars finally reach the end of their hydrogen reserves, trillions of years in the future, they are predicted to undergo a unique transformation. Instead of expanding into red giants, they will become hotter and smaller, turning into hypothetical objects called blue dwarfs. These blue dwarfs will be much more luminous than current red dwarfs, marking the final bright phase of the stelliferous era, the age of stars. They will be the last major sources of energy in the universe before it begins to fade into darkness. Once the last bits of fuel are exhausted, these blue dwarfs will finally collapse into white dwarfs, joining the billions of other stellar remnants already cooling in the void. These white dwarfs will then begin the incredibly slow process of cooling down until they reach a state where they no longer emit any detectable light or heat. At this point, they become black dwarfs, cold and dense balls of degenerate matter that are effectively the ashes of the stars. The time required for a white dwarf to become a black dwarf is so vast that the universe is not yet old enough for any to exist. These objects will eventually be the only matter left in the galaxy as the era of starlight comes to a final, permanent end. Brian Cox has described this as the transition to the degenerate era, where the universe becomes a cold and empty void, and the arrow of time as we understand it effectively disappears. This final fate is dictated by the laws of thermodynamics, specifically the increase of entropy, which states that all energy will eventually be spread out uniformly. In this future, entropy can no longer increase because the cosmos cannot get any more disordered, and nothing ever happens again. The universe will be permanent and unchanging, a dark sea of photons cooling toward absolute zero. It is an inescapable fact written into the fundamental laws of physics. However, this dark ending also highlights the preciousness of our current era. We are living in a tiny fraction of a percent of the universe's total history where life is actually possible. The light of the dwarf stars that we see today is a fleeting gift, a moment of complexity and warmth in an otherwise dark and silent eternity. Our lives, our civilizations, and our search for knowledge are all happening during this golden age of starlight. The dwarf stars, from the long-lived red dwarfs to the final black dwarfs, map out the entire history and future of the cosmos. They are the chronometers of the universe, and by studying them, we can see the full scale of the time we have been given. They remind us that while the universe is vast and its destiny is dark, the current era of light is a wonderful mystery that we are privileged to witness and understand. The exploration of dwarf stars reveals a fundamental truth about our universe. that the most common and unassuming objects can hold the most profound secrets. They are the bridge between the vibrant, light-filled era we inhabit today and the cold, dark, and silent era of the far future. From the dense quantum fortresses of white dwarfs to the mysterious rogue worlds drifting alone, these stars define the boundaries of stellar identity and the evolution of the cosmos. Carl Sagan's reminder that we are made of star stuff is more than just a poetic sentiment. It is a direct biological and physical link to the nuclear synthesis occurring in stellar hearts. Every atom in our bodies was forged in the same processes that we now observe in distant systems like Gliese 229b or W. D0525 plus 526.1. This connection makes the study of dwarf stars a study of our own origins, a way for the universe to look back and understand its own creation through us. The anomalies we have explored, from the over-luminous enigma of C.W. 89ab to the chaotic polar orbit of 2M1510, show that our scientific journey is far from over. These gaps in our mathematical models are not failures, but opportunities to refine our understanding and to uncover deeper laws of physics. They remind us that the practice of science happens at the border between the known and the unknown, and that the universe still has many ways to surprise us. The predictive power of modern astrophysics allows us to look trillions of years into the future, mapping out the transition from red dwarfs to blue dwarfs and eventually to the dark silence of black dwarfs. We can see the ultimate fate of the Milky Way and the eventual heat death of everything that exists, a testament to the power of human reason and the precision of our mathematical tools. This knowledge provides a perspective that is both humbling and exhilarating. As Brian Cox often reflects, the fact that we can understand these things makes our existence incredibly precious. We are the cosmos made conscious, a brief moment of awareness in an eternity of silence. The light of the stars that we see today is a messenger from the past, carrying the story of the universe's origins to our eyes and our brains. We have the responsibility and the privilege to continue seeking the answers to these cosmic mysteries. The final legacy of the dwarf stars will be their endurance. As our own sun eventually collapses into a white dwarf, it will carry the chemical signature of Earth and human history into the dark for trillions of years. We will be a silent, diamond-like monument in the void, a testament to the fact that for a brief moment in time, there was life and curiosity in this corner of the galaxy. Our chemistry is our ultimate legacy, preserved in the hearts of the stars. We conclude our journey with a sense of wonder at the quiet destiny of the cosmos. The universe is a vast, beautiful, and often chaotic place, yet it is governed by laws that we can begin to comprehend. The dwarf stars are the guides on this journey, showing us where we came from and where we are going. They are the enduring remnants of the past and the silent harbingers of the future, holding the keys to the most profound mysteries of the sky. Standing on the shoulders of giants, we continue to peer into the darkness, not in fear but in the pursuit of truth. The stories of Gliese 229b, W, D, 0525 plus 526, and I, L, T, J, 1101 are just the beginning of a much larger exploration of our galactic neighborhood. As long as there is light to follow, we will continue to journey from the confines of our planet to the furthest reaches of the Milky Way, unraveling the mysteries of the stars one pulse, one spectrum, and one discovery at a time.